Hello, I'm Brady Thomas, and this is Lab 4 Oscillations. So to introduce this lab, our main purpose was to examine the motion of a spring mass system in which a mass swings in an arc while also oscillating, and then to create a computational model to replicate this. So the models we used were a tracker motion capture data and then glow script code for the spring mass system. And the main fundamental principles we need to focus on are springs, both their force and potential energy, the force of gravity, Newton's second law, and the energy principle. And our main result was that we did succeed at replicating the motion within our coded model. So for our important physics concepts, we first have to remember Newton's second law, which is F net equals change in momentum over change in time. And from this, we can derive our important equations as the velocity update equation and the position update equation, which we have to use within a loop in this code like the rest. As for forces in our system, we have to use the force of gravity, which is just negative mg in the y direction, and then we also need the spring force, which is negative k, the spring constant, and then we have our current length minus the relaxed length, and then we multiply that by our L hat, which gives us our directionality. And then we can find the F net at every point for our system by adding these two together. Finally, we need to pay attention to the energy in this system. So we're using the system including the spring, the mass, and the earth. So all the energy involved is the kinetic energy of the mass, which is 1/2 mv squared, the spring potential generated from the spring, which is 1/2 k times the stretch or shrink squared, and then the gravitational potential, which is mg times y, or our height. And so since we are putting all of these on one side, those will all be our change in energy. And our change in energy is equal to work plus our heat. But in this case, since there's nothing else in our surroundings, there's no work or heat, meaning our change in energy should be 0. So for our tracker data, we are tracking the mass on the spring, and the actual mass that we found this was 0.402 kilograms. And then using the data, we were also able to find our relaxed length of the spring, which was 0.123 meters, and also the spring constant, which is 6.83 newtons per meter. And also in this video, we're assuming that there's no motion towards or away from the camera, and that it's just restricted to this like XZ, XY plane. And so there you can see in the video the actual motion where it kind of oscillates left to right as well as up and down. And we tracked this right at the release, so then we also didn't have to account for the initial velocity. Okay, so this represents our coded model. Our code, at the beginning, you can see we initialize some things like the equations for the energies, but most of it is surrounding this huge while loop. And so the while loop is for under 9.5 seconds, since this was the length of time that we recorded the data for in Tracker. And so within this big while loop, we can update our velocity, position, and force for changing spring force, even though gravity force stays constant. As our spring stretches and compresses, our spring force will change and its direction will as well. Also, within this loop, we update our energies, including kinetic, gravitational potential, spring potential, and then we can find the change in total energy calculated between each iteration by subtracting it from the previous step's energy from the current. And then this loop resets with time updated by 0.095 seconds, which was the time for a video frame in our experiment. So comparing our tracker and our coded data, they came out very, very similar. And there are only slight variations, which I would assume are due to things like real-world interactions in the experiment, like some energy being lost through heat and sound, which is why the peaks for those lows and highs in the oscillations aren't quite as extreme. In terms of the rest of the output from our code, we can see the shape that the actual oscillations make on the top there, and it looks very similar to the ones seen in the video. And then we have our energy graph, in which we can see the forms of the energy change up and down, such as our kinetic energy or our gravitation or our spring energy, but they all balance out so that our change in energy stays at 0. So for the what does it mean questions for our model system, is the energy principle satisfied? We can say yes because our change in energy observed in the energy graph was 0 because the Earth, spring, and mass are all in our system, meaning that there's no energy exchange or forces outside of our system. And finding our oscillation periods in the x and y direction, we found in the x direction it was 1.63 seconds, and in the y direction 1.52 seconds. And we can say this is probably because there was more force in the y direction than the x direction.